Hello friends, we'd like to continue with the part 2 of the video. We had talked about channel estimation techniques. Next, we would like to go to peak to average power ratio, which is one of the important parameters to be considered for orthogonal frequency division multiplexing. First, I would like to explain what exactly is peak to average power ratio. As you can see, PAPR signal is expressed as 10 log of maximum x of t, that is one take just consider it as a complex tone signal which is defined in the next statement. This term is a conjugate of the complex signal. So if I consider the peak value, PAPR is basically the ratio and logarithmic ratio of the maximum value of the product to the mean value. Now if I consider a complex tone signal as defined here, the peak value of the signal can be obtained as follows. That is, when the power of the exponential is 0, that is the value maximum power that can be attained is 1 for this signal. The next one is, after defining the numerator, we like to define the denominator if I have to find the mean square value of the signal. Similarly, if I consider the mean square value, it is also 1. So the ratio, the maximum value that peak to average power ratio can be taken is 0 dB, that is 10 log of 1, that's 1 by 1, just we calculated that. Now if I consider an OFDM signal that is having k number of subcarriers, so what exactly will happen? Let's see that. An OFDM time signal made of k complex tones can be represented by this formula. This x of t is summation going from 0 to k minus 1, a of k, that is just a constant, exponential j 2 pi kt by t, where t, capital T, is the time period. We'll just use the same formula. We'll just replace the complex tone signal used previously with the newly defined signal. As you can see, if when I substitute the appropriate values, we get the numerator as k squared. Similarly, if we find the mean square value of the signal, its value is k. So what exactly is the problem? So if I consider the ratio of these two, that is k squared by k, so it has the value we'll obtain is k, which means that as the value of k increases, in short, as the value of the subcarriers, number of subcarriers increases, this parameter will affect the signal more and more, which is not as required by us. So what exactly can we do to overcome this? We have a number of reduction techniques like block coding techniques, selected mapping, partial transmit sequence, interleaving technique, tone reservation, tone injection, clipping, and filtering. So let me go through some of the reduction techniques to better understand the concept. The block coding technique. The fundamental idea is that of all the probable message symbols, only those which have low peak power will be chosen by coding as valid code words for transmission. There will be no introduction of distortion to the signals. For example, if we have n subcarriers, they are represented by 2n bits using QPSK modulation and thus 22n messages, using the whole message space corresponding to 0 bits of redundancy. Using only half of the messages corresponds to 1 bit of redundancy. The remaining message space is then divided in half again, and this process continues until n bits of redundancy have been allocated, which corresponds to a rate 1/2 code for n subcarriers. Large PAPR reduction can be achieved if the long information sequence is separated into different subblocks and all subblock encoded with system on a programmable chip. Now the next one is I like to go to the interleaving technique. The notion that highly correlated data structures have large PAPR can be reduced if long correlation pattern is broken down. This is the basic the idea behind using interleaving technique. Its adaptive interleaving is to set up an initial terminating threshold. PAPR value goes below the threshold rather than seeking each interleave sequences. The minimal threshold will compel the adaptive interleaving to look for all the interleave sequences. The main importance of the scheme is that it is less complex than the partial transmit sequence, which will be discussed in a short while, technique, but obtains comparable result. This method does not give the assurance result for PAPR reduction, so it is not used to the extent as the partial transmit sequence, or you say clipping and filtering. We like to go through tone reservation. The main idea of this method is to keep a small set of tones for PAPR reduction. This can be originated as a convex problem, and this problem can be solved accurately. Tone reservation method is based on adding a data block and time domain signal. A data block is dependent time domain signal to the original multi-carrier signal to minimize the high peak. In this way, we can reduce the PAPR by using the tone reservation. Next, we'd like to go to the tone injection method, which has been recommended by Muller, SH, and Huber, and JB. This technique is based on general additive method for PAPR reduction. Using an additive method achieves PAPR reduction of multi-carrier signal without any data rate loss. The main idea behind this method is to increase the constellation size such that each point in the original basic constellation can be mapped into several equivalent points in the extended constellation. Since all information elements can be mapped into several equivalent constellation points, these additional amounts of freedom can be utilized for PAPR reduction. The drawbacks of this method, however, are that it needs to cite information for decoding signal at the receiver side and cause extra IFFT, which is the inverse fast Fourier transform operation, which would be more complex for this technique. The last and most commonly used and most simple technique is the clipping and filtering. One of the simple and effective PAPR reduction techniques is clipping, which cancels the signal components that exceed some unchanging amplitude called the chip level. However, clipping yields distortion power, which called clipping noise, and expands the transmitted signal spectrum, which causes interfering. Clipping is nonlinear process and causes in-band noise distortion, which causes degradation in the performance of bit BER, that is bit error rate, and out-of-band noise, which decreases the spectral efficiency. Clipping and filtering technique is effective in removing components of the expanded spectrum. Although filtering can decrease the spectrum growth, filtering after clipping can reduce the out-of-band radiation, but may also cause some peak regrowth, which the peak signal exceeds in the clip level. The technique of iterative clipping and filtering reduces PAPR without spectrum expansion. However, the iterative signal takes long time and it will increase the computational complexity of an OFDM transmitter. But without performing interpolation before clipping causes it out of band. To avoid this out of band problem, signal should be clipped after interpolation. So these are some of the reduction techniques that I wanted to talk about regarding the peak to average power ratio. Next one is error correcting codes that we use. Some of the commonly used error correcting codes are turbo codes, convolutional coding, LDPC codes, which I like to talk about. So OFDM is basically invariably used in conjunction with channel coding and almost always uses frequency and or time interleaving. So what exactly is frequency or time interleaving? Frequency interleaving increases resistance to frequency selective channel conditions such as fading. For example, when a part of the channel bandwidth fades, frequency interleaving ensures that the bit errors that would result from those subcarriers in the faded part of the bandwidth are spread out in the bit stream rather than being concentrated.